这没差，反正它只要跟你用对。那我们都是讲到第三条，
So last time we started to talk about Locus. When we started to talk about Locus, some of you guys might ask you what this really means. This one is used to determine the range of the K of your controller, how much K you should put in your controller so your system can still be stable. So when we are drawing those kind of stuff, there are a few things you guys need to remember. Typically, we are having our system look like this. So when you start to put everything together as a closed loop system, we are going to have the system look like this. And we say if we start to sketch our locus, the pole over here is actually start from open loop poles and let's start from open loop poles. So you're going to start to plot all the poles anywhere you want to and all the zeros you have in your open loop system. Then since we have our controller, you might have KB, KP, and KI. Locus can only determine the movement of your poles based on one single variable. It can be a variable of KD, KP, or KI. So far, we just use one K, which is P controller. So when your KP start to change, you're going to find out, you're going to observing that the pole is going to change its location because the closed loop pole is going to be different based on different poles. Okay, based on different gains. Okay, so it might start to. Last time we are using this example, so it might goes up, goes down. That is when my K increase, right? And we say it's going to be end at 0. When we do not have any zeros, it means that we have an arbitrary 0, which is located at infinite distance. So that's the reason they are going to somewhere that goes to infinity. If you have 3 poles, we say we need to find something which is the centroid and draw the asymptotus. So one pole is going to follow the individual asymptotus accordingly. Depending on how many poles, how many zeros you have, you're going to determine the angles based on the number of poles minus zeros. If you have higher orders, this one can be weird, but do not worry about that. If it's in the test, I'm not going to give you higher than 3 order, 3rd order, 4th order. I won't give you more than 45 degrees or anything like that. If you find out I give you more than 5th order, it means that some of you guys piss me off, and I really want to fail some of you guys in the test. Normally, I won't do that. Don't worry. Okay, but that is something you need to know. So there are a few things we have been talking about. Let's see. Okay, the first thing we need to know is we're going to have plus minus 180 degrees divided by the number of poles minus the number of zeros. And this is going, I'm sorry, this is the angle. It should be, what is the formula? It should be that's the number number of asymptotes we're going to have, and we have angles. That is going to be theta A equals to plus minus 180 degree divided by this number over here. Okay, that is another thing we have been talking about. And the next one is centroid. That is going to be no A equals to the value of poles minus the value of zeros divided by MP minus MZ. Okay, so how many poles minus how many zeros, and the position is going to be a centroid, one-dimensional centroid. So this is something we're going to have for asymptotes, angles, and centroid. So we have been talking about this last time, and we talked about magnitude criterion and angle criterion. That is going to be used in controller design. You don't need to worry about that right now when you join the Locus at this moment. We're going to use this one later when we start to design the controller, but it's just some kind of introduction. I need to tell you what to do in 7.2.1 in the analysis part. Yes? Huh? Open loop pose. Open loop pose means that if you do not close loop everything, this is going to be your open loop. You have two transfer functions. One is your controller. One is your plate or your machine. Okay, so the open loop is your system response. If you don't have any controller, if you don't have any feedback from your system, then it's going to be open because the loop is not closed. So we call it open. Initially, yes. Yeah, initially, yes. We need to see this one, and this one. They are open loop holes. That's a good question, because when you try to sketch something like this, sometimes your system can be very weird. Something like you don't need to write down this one. This is just one of the examples. That's not good. Let's not do this one. Something like this. So if you have something like this, you don't need to draw this one. I just make it up. So I don't even know what the transfer function this one is. But when you have this block diagram over here, you're going to find out your closed loop is going to be one format like this denominator, right? You must have something on top of this one, and in the bottom over here. Since it's closed loop, you're going to have one, no matter what. One plus something, and this is going to be your open loop transfer function over here. Does that make sense? It can be anything depending on what this one is going to be. Normally, our closed loop system is going to look like this one. That's very typical system design. But sometimes, because some different engineering design something weird, then you might have weird block diagram, and you have no choice but generate your transfer function based on the block diagram. But it doesn't matter what you do. If you want to find out Locus, this is going to be your open loop transfer function, and you must identify the overall transfer function before you can determine what is the open loop transfer function you want to put in the Locus. Okay, I'm not going to give you something like this in the test because it doesn't really make any sense to me. However, when you read the example or other things in particular you're going to, some of you guys might take the entrance exam in the future. This might be something people feel interested, though I don't like it. But when I say I don't like it, I'm not going to put that in the entrance test if I'm the one who designed the problem. But this is something you need to know. What this one is, why I use this one, okay? It can be open loop for anything, but the open loop transfer function over here is you use plot diagram to identify what is the transfer function between input and output, and use this part over here as your open loop transfer function and start to generate your locus. Does it make sense? It's just like a mathematical tricks. Anyway, so we got three things over here: asymptotus, angles, centroid. Next thing is we're going to talk about breakaway and breaking points. Okay, go back to this one. Over here, we know the angle is determined by one of the formulas, theta A. The position over here is the centroid. We know this one and this one. But how about this point over here? This point, because we have few zeros over here, so we know they might hit or encounter with each other and start to break out, right? Because it must end at infinity, which means it will get close to each other and start to break out. This point over here is we call breakaway, because they are leaving from the encounter to other directions. Does it make sense? So it's break away. If you have some other things, like you have 0, like this, they will, in this case, I have 2 poles, 1, 0, right? So if you use the determinations, the equations over here, you know we are going to have only one asymptotus. Only one asymptotus, right? And that must be negative or positive 180 degrees, which means it must go to that direction. Make sense? And one of the pole is going to be attracted by this 0, and the other one must go to what? Infinity, right? And that is going to be negative 180 degrees. So we know it must go to this direction, right? So, and they cannot be intersect with each other. That's a rule. It must be symmetric. So they must go together and break out or break away. And after they hit these points, one is going to be attracted by the 0, the other one goes to infinity. This point over here is break away. This point over here is break in. One is goes in, the other one goes out. Should be pretty straightforward, right? The definition over here should be pretty straightforward. Now, we need to have formula to come up what's going on over here. How are we going to find out a number of this point and this point? Okay, so normally you have your poles. If you have your poles and you are going to see they will get close to each other and they will break away at this location. This one over here, we're going to set dk over ds equals to 0, 1. When we say we want to have a differential of one number, it means that I'm trying to find out my local maximum or local minimum. So when we do that, K is the relative maxima with respect to S. Okay, so this one over here is if we just put everything as a function of K, put K as a function of S, then we differentiate everything and set the equation equals to 0, then we should be able to find out this number. In many cases, you're going to have quadratic equation or higher order. If you have quadratic equations, it means that this differential equation is going to have two answers. If you break out over here, the other one must be breaking. Does that make sense? So if you have breaking, typically they are going to be attracted by zeros. So it means that it will get from someplace and breaking. One goes to one pole and the other one goes to the other direction, attracted by another pole. This point over here is breaking. Still, we will have to set the K over the S equals to 0, but that one over here is local maximum. K in this case is going to be local minimum. Relative. Over S. Any question? So take a look at this one. My question for you guys: do a system, do the rule Locus for higher order equations, how many break-in or breakout points I can have in a system? Can I only allow, do I only allow to have one break-in or one breakout? Or can I have multiple break-in and breakout depending on my characteristic equation? First one, second one. The answer is second one, because you might have, there are some weird configurations. You're going to have multiple break-in and breakout, and that is something we're going to talk about when we design some weird controllers. You're going to see the Locus is really weird, and you might not be able to see those kind of stuff visually because they are too close, and the break-in and breakout is actually too small, and you cannot notice that. But it doesn't matter what you do. Keep in mind, this is the solution of differential equation. If you got higher order, it means that you might have multiple answers over here. When there's multiple answers, it means that you must have multiple break-in and multiple breakout, depending on how you design your system. And if you are lazy and you don't want to do anything, just use. This will do the trick using MATLAB. Okay, I think next homework I'm going to ask you guys to do Locus. Okay, any question? Yes.
是 ds。
You can put, because it might have something like just one of example. So you put k equals to, then differentiate this one. So differentiate this part with s. So you get another polynomial. Find out the answer of the polynomial. That will be your dk over ds. Okay, we're going to do one of the example over here. So this one we have been talking about that many times. So clearly, I'm telling you, this is my open loop transfer function. So I have two poles, no zero, which means I'm going to have, I'll do 0 over here and 1 over here. Okay, and we know this one. First, we determine our poles. That is something we draw on the S domain. Secondly, I have two poles. I have non-zero, so the thing over here is going to be 2, which means I can determine my theta A. That is going to be plus minus 180 degree divided by 2, so it's going to be plus minus 90 degree. Which is not a news because we have done this example many times already. So it's going to be plus 90 minus 90, right? And the central is going to be minus 1, minus 0 because those are the locations of my poles, and I don't have any zeros, so I don't need to worry about this part over here divided by 2. So it's going to be negative 1 over 2. So the centroid is going to be located over here. So we can start to draw our asymptotus over here. My k s plus 1 equals to 0, which means I got my k equals negative s plus 1. Everybody understand how I get this one, right? You just move 1 to the other side, which becomes negative 1. Negative 1 multiplied by the denominator over here is going to be negative s plus 1. Is that straightforward? Everybody understand what I'm talking about? Yeah? And that's 1 over here. Because it's a closed loop transfer function, the characteristic equation. We are talking about this one. So I have a plus 1, and that is this one. This one is this one, and 1 is this one. So we need to have that plus 1. So if I move 1 to the other side, it becomes negative 1. Multiplied by everything becomes something like this. So the next thing we're going to do is dk ds. That is going to give me negative 2s minus 1. What I need to do is to equalize this equation as 0. So can you tell me what is the answer for this equation? Negative 1/2, right? So it's going to be overlapped together with the center. And based on the observation, do we have poles or zeros in my S domain? Do I have any zero?
No.
So should I have breakaway or breaking?
Breakaway.
How many points do we have? How many points do we have?
One.
Just one. That is going to be negative 1/2. Right. So you can start to draw things with confidence. Again, I don't know whether this one goes up or down. It's just an approximation. But I certainly know it's going to be goes to this direction, goes to this direction, goes to this direction, and break up. Any question? Yes, question? No. You'll see. We're going to talk about that later. Some of you guys might say, okay, they should be overlapped all the time. The answer is no. It's like this is because we designed this one over here. But if you have any other post on the other way, and you get another post somewhere, this can be shifted, right? Because the centroid is going to be affected by other poles and zeros. For instance, if I have one post and one zero over here, we certainly know they're going to be attracted. This one is going to be attracted by this one, and those two still goes to infinite, right? But because I have a large number of poles, I have a large number of zero. So we might shift our centroid toward to this direction. In this case, even though we know the breakaway point might be something like this, but it can be one goes here, the other one goes here. Because the centroid has been shifted. But the breakaway point is going to be needs to be calculated accordingly. And it might go to this direction and this direction with some kind of curvilinear approach. Does it make sense? That would be something we're going to see later when we are designing other part, when we are talking about other part of the locus. Before we move on, the other thing that we might wanna consider is, okay, I know it's going to be breakaway over here. So at this point, what is my K? Then we use this magnitude criterion. This one is used to determine, well, if I have specific location on my S, what is a K is going to look like. So based on angle criterion, this is the formula that we have. This is the absolute value together with the poles. This part over here is magnitude, absolute values together with zeros. It's just upside down. This is zero, this is poles. And K is just the inverse of this one because that is also based on this one. We take everything. Absolute, this part is going to be 1. So if I have K on one side, this one on the other side must be something like this, just opposite. So far, do you guys still remember what I'm talking about? because we're talking about magnitude. There are two things for our complex numbers. One is magnitude, the other one is phase. Over here, phase is something we're going to discuss later. Over here, I try to find if I have my Locus loop like this, and I know it's going to be breakaway at s equals to negative 1.5. So if I have my location over here, can I identify how much k I have over here? So if we do that, this is the formula we're going to use because we're talking about magnitude. And we try to find what is my k. When we try to find the k is a gain, and it's going to affect my magnitude. So I'm going to use magnitude criterion to identify what my k is going to be. Since I know my k, my s in this equation, in this specific example, is going to be breakaway at negative 1/2. So I can just put how much I'm going to have. So k is going to be, we talked about this last time, right? So when it's greater than 0.25, they were going to be encountered with each other. So you can use magnitude criterion to find out those things. If you have k equals to negative 0.5, they are going to have, we're going to have the double roots located over here for the closed loop transfer function. Does it make sense? Everybody understand what I'm doing? It's confusing, right? Yeah, I think it's confusing because you need to figure out what I'm talking about. We can go back to, well, I think you might need to understand what I'm talking about, so I'll spend more time over here. So when we are doing closed loop transfer function, I'll have right? So if I simplify the transfer function over here, I'm going to have k. Over here, I'm going to have s squared plus s plus k over here. So if I say my k is 1/2, that is going to be my polynomial for the denominator for my closed loop transfer function. So if I find out the roots of this specific polynomial, what do I find? I find out my poles with this k on my S-plane. Make sense? So if you take the roots of this one, you're going to find this is s plus 0.5, s plus 0.5 because of this specific polynomial. Which means if I have my k equals to 0.25, I'm going to have two poles located at the same position when I close loop my transfer function, which is going to be over here. So you can use those kind of things to verify where your k is going to be located. Either use the formula, angle criterion, or you just calculate everything point by point. But of course, we don't want to do this one because it's going to be tedious. Every time you change your pole location, it's going to be changed. And if you know this one, you still need to know what is your k before you can verify that. So normally we do not want to do this part because it's going to be point by point. And it's going to be a lot of calculation and we don't want to do that. So we can just use magnitude criterion to identify what is the, when they are hit together, what is my k. Does that make sense? good question. K must be positive because we don't want to drink our system. If you put your K to be negative, a lot of time you're going to make your system unstable. The reason is if you have your K equals to -1, what happens? What is your polynomial over here? What is your system? Are your system going to be stable or unstable? Unstable, right? So that is the reason we don't want to have that mathematically. The other one, if you want to think about one physical operation, psychologically, everybody know what I'm going to do, right? So my girl is punished, and because you know little girls, and because she breaks some rules at home, and I just told him, okay, I'm not going to give you candy for today. She started to cry. When she started to cry, I'm telling her, if you cry more, you don't have candy tomorrow. What happened? Cry more and louder. If you keep on crying, you won't have candy for the next week. What happened? The house will be torn down because the voice is too loud. Right? That's positive feedback. Psychologically, everybody understand what I'm talking about, right? Okay. Now, a physical thing is speaker. Microphone. So what is microphone used for? Amplify our sounds, right? So and your amplified sounds is going to be what? Put into your speaker through an amplifier. If you put this one close to your speaker, what happened? Everybody got this kind of experience. It starts from original you doesn't sound anything, but if you just put the noise on the microphone, this one is going to increase the volume until infinite. Right? And everybody will tell you, turn off the speaker. That is positive feedback because you got a small thing over here, then you multiply by 2. Then go back to this one, it says multiply by 2 again, so you multiply by 4. And you keep on going, so it's going to be positive feedback. And that is because you have a positive thing over here, negative thing over here, so everything goes back to the system, becomes positive feedback. So you're going to make your system unstable. Okay? So you guys understand psychologically and physically what this kind of things is happening, right? So you don't treat your significant another. You know significant another means? Significant another means 你的另一半，或是你的女朋友，或是你的男朋友. Do not treat them with positive feedback because your relationship becomes unstable. Okay, everything can be controlled under control theory. You need to have negative feedback and keep everything stable. Do not put your pulse or your excitement on this side, otherwise you're going to get trouble. And how do we calculate for the tolerance? We can use the tricks we're going to introduce later to find out what is a K that is going to cross the boundary. You do not cross the boundary, so everything is it's going to be stable. Five minutes. I'm going to say one more thing. This time, because so far we have all our poles located on the real axis. But if you have complex poles or complex zeros, what happened? So let's say I have complex zeros over complex pole over here, and I got the real zero over here. So we might say I want to have my water away. Sometimes it's going to be closed loop. Poles. Depending where you want to have it. So if you connect this one with all the poles over here, it can be even, it can be the closed loop poles, and you start to calculate the angles. Then you are going to have your Z. Let's talk about this one later because I don't think I have time to explain that. Any questions before we move on? Before I let you guys go? I need to take at least 10 minutes to explain this thing. So I don't think it's a good idea just let you guys do something over here. Any questions before I let you guys go? No? Okay. You guys have a nice weekend. Thank you.